So, today I will discuss about Zeeman effect and I will demonstrate the same in our laboratory. So, the Zeeman effect, it was discovered by Peter Zeeman in 1896 and he got Nobel Prize probably in 1902 for this discovery. So, fundamentally this effect is very important. So, let us understand the effect first and then we will demonstrate in our laboratory. So, Zeeman effect basically when we apply magnetic field in atoms, so the spectral lines split it. So, in presence of magnetic field the spectral line split it, that is basically Zeeman effect. So, effect of magnetic field on spectral lines, that was discovered by the Zeeman. So, you know the spectra of atoms, forget magnetic field, just spectra of atoms, that is electronic transitions among energy levels. Electron goes from one levels to another energy levels. So, because of that there are emission of electromagnetic wave. So, that is depending on the wavelength. So, wavelength dependent the pattern we get. So, that we tell the spectral lines. Okay. So, in atom there are energy levels. So, this energy level we designated by this principal quantum number. So, n equal to 1, so we tell k shell, n equal to 2 we tell this is L shell, similarly M shell. Okay. So, these have energy. So, now another quantum numbers, that is orbital angular quantum number L. So, because of L, so these levels are again splitted. So, then we tell this is orbitals or subcells S, P, D, F. So, L equal to 0, 1, 2, 3. Okay. So, then this energy level again it is splitted because of the spin of the electron. So, that spin angular quantum number, that is basically S. So, for electron S is half. So, this line again due to the spin it may split into each line, it may split into 2. So, this is we tell MS, magnetic spin quantum number MS. MS is plus up and minus up, plus up and minus up. So, each energy level again it can be splitted into 2. Okay. So, whatever splitting I am talking, so splitted energy level, so their energy may be same, then we tell that degeneracy. If their energy are different, splitted energy levels, their energy are different, then we tell there is a degeneracy is removed, non-degenerate state. Okay. So, now this L again it is splitted because of space quantization. So, that is designated by another quantum number. So, that is called magnetic orbital quantum number. So, that is ML. So, this L it can be splitted L equal to 0. So, it is a ML is 0, L equal to 1, ML is 0 plus minus 1. So, it is splitted into 3. Again I am telling that the energy can be same or it can be different. If same, then we tell degenerate states. If different, then we tell non-degenerate states. Okay. So, that depends on the situation, depends on the atom, depends on other factors. So, quantum number, here we are seeing this principal quantum number, orbital angular quantum number, then spin angular quantum number. Okay. So, these three basically the quantum number which we use for designating the electronic state of electrons in an atom. So, now there are two space quantization, one is for orbital angular momentum and another is for spin angular momentum. So, about a orbital angular momentum, so it is rotating on a ellipse or on a circle. So, this is on a plane. Now, whether this plane can be rotated in space, okay, whether it is allowed. Yes, in principle it can be any plane, but it cannot take any plane. So, that is it is quantized, it is basically quantized. Okay. So, when orbital is moving on a plane, so this direction of the angular momentum is basically perpendicular to this plane. So, now, so this is also quantized in space. So, that we express with this quantum number ml. So, this ml value, it is basically about a fixed direction in a space. So, what is the projection of the direction of the orbital angular momentum on this fixed direction? So, this if you take the projection on this fixed direction, so this length is basically it is expressed by ml. So, this is basically L cos theta, you know, ml is basically L cos theta. Okay. So, when this it is 90 degrees, so its projection is 0, so ml is 0. Okay. So, if it is in this direction, so it will be ml will be 1, ml will be 1 because cos theta is now 0 angle, it is 1. So, it is opposite direction, it is the 180 degree. So, cos theta is minus 1, so ml is minus 1. Okay. So, it is basically projection cos theta value on a fixed about a fixed direction. So, why it is called similarly the spin angular momentum. So, it also quantized in space. So, it is quantized in two direction, either up or down. Okay. So, that is expressed by plus up or minus up. So, why it is called magnetic quantum number? It is called magnetic quantum number because this in space we are considering a reference direction. So, generally in space we apply, if we apply magnetic field, so we apply in a particular direction. So, that now reference direction is the direction of the magnetic field direction. Okay. So, that is why it is called magnetic quantum number. Now, so you have two angular momentum L and S. So, now these two angular momentum they are not always, they are not independent, they coupled with each other. Okay. So, that then one can find out the total angular momentum. So, that is basically J, that is basically J, J is the total angular momentum. J, it can basically vector addition of L and S. So, it can take value L plus S to L minus S, okay, in between just difference L plus S minus 1, L plus S minus 2 up to L minus S. But I have taken mod, always it is positive value, because negative value we do not take, because negative value is taken care by the projection by mj. Similarly, this here this for L there is a space quantization ml ma, similarly mj. Okay. And Gj is basically Lagrange factor. So, the Gj is equal to 1 plus j plus 1 plus s plus 1 minus l plus 1 divided by 2 j plus 1. So, in case of this orbital angular momentum, so there also Lagrange factor is there. So, there we write GL. So, GL value is 1, GS its value is 2, and GJ its value depends on this, okay, L, S and J. Okay. So, one can for here if uh, if this one L equal to 0 and this one say L equal to 1. So, S equal to half for a 1 electron. So, J will be L 0 and S half. So, J will be half. L 1 J I think I have taken here L 0 and L 1. So, again L 0, so it will be J half, L 1 it will be J half and J 3 by 2. Okay. So, depending on the spin orbit coupling, so there will be splitting of the energy levels. Okay. So, further this again splitted due to the space quantization. So, this is the basically mj. For defined mj value it is again splitted. So, you can see here, so there are different quantum number. So, depending on the quantum number or using the quantum number, we can basically see the splitting of energy level. It is a particular energy level, it is splitted into many energy levels. So, their energy may be same or may be different. Okay. So, depending on the situation. So, in a atomic system there are many energy levels. Now, transition among these energy levels, transition of electrons among these energy levels gives basically the electromagnetic wave of different wavelength. And if you see this in a spectrometer, if you see this light, you will see, you can separate the wavelength and that is basically we tell the spectra. Okay. So, this is the without any magnetic field atom can give spectral lines, and in spectrometer we can see the spectral lines. So, in case of hydrogen atom, it is the simplest atom, is the simplest atom. So, energy levels are there. So, you know this n equal to 1, 2, 3, 4. So, transition from higher levels to 1 it gives Lyman series, transition to n equal to 2 from higher energy level, this give Balmer series. So, in Balmer series H alpha line, H beta line, H gamma line. So, H alpha is basically 3 to 2, that transition it gives this H alpha line. So, if I take this H alpha line transition between n equal to 2 and n equal to 3, now this is n equal to 2, n equal to 2. So, it will have basically this say if this is one spectral lines, if it is one spectral lines without any magnetic field, if we do not apply any magnetic field, now this if we apply strong magnetic field, these spectral lines will splitted into many lines. Actually, what happens here? So, when you apply magnetic field with respect to that direction, now this magnetic moment of the this electron which involved in this transition. So, basically it will be oriented, it will be its angular momentum will be oriented in space. So, there this ML is coming into picture. Okay. So, ML, so n equal to 2 means L equal to 0 1. So, ML will be 0 plus 1 minus 1. So, it will be split into 3 lines in presence of magnetic field. Okay. So, n equal to 3, L equal to 0 1 2. So, ML will be 0 plus minus 1 plus minus 2. So, it will be split into 5 lines. Okay. So, here 2 energy levels. So, due to transition 1 lines you are getting. Now, these energy levels in presence of magnetic field it is split into here you can see 3 and here 5 8 lines. Okay. So, then there will be lot of transitions among them following the transition selection rules, del L equal to plus minus 1 and del ML equal to 0 plus minus 1. So, you will see many transitions, but here this energy separation, in this case this energy separation for delta ML equal to 0, for delta ML equal to plus 1, delta ML equal to plus minus 1. If you see this here 9 transitions are there, 3 of them are for del ML equal to minus 1. So, they will have the same energy, these 3 lines will have the same energy, other 3 line for del ML equal to 0 it will have same energy, and these other 3 lines del L del ML equal to plus 1. So, it will have different energy. So, actually these 9 lines we are seeing that will be basically, this is basically we will see 3 lines, 3 spectral lines, 3 different wavelengths. Okay. So, as if here what you are seeing, in absence of magnetic field there is a one spectral lines, but when we apply strong magnetic field that one line is splitted into 3 lines. Out of these 3, one is the original one. Okay. And other 2 will have the different energy, other 2 will have the different wavelength, other 2 will have the different frequency. Okay. So, as if one line is splitted into now 3 lines. So, this is called basically normal Riemann effect. Okay. So, here H alpha one line I told, but it is not correct. This H alpha line it consists of more than one line, it basically consists of 5 lines. Okay. So, that is basically fine structure, that is basically fine structure of spectral lines, but they are very closely spaced. Okay. So, however, so H alpha line if you consider the LS coupling, so then energy level without magnetic field energy level will be like this, and so we will get basically 5 spectral lines. So, their wavelengths are very close. So, H alpha line is not one line, it is basically 5 line. So, if you pick up or if LS coupling is not there, so L and S are independent, then basically you will see the 3 lines. Okay. Or if you apply here I have written with strong magnetic field, not with weak magnetic field. Why the strong magnetic field? So, basically when we apply strong magnetic field, then LS coupling will break. Okay. So, there will not be coupling between L and S. So, then basically instead of 5 lines, so it will have the 3 lines, Now, each line will split it into many more lines, So, here each line will be split into 3 lines. When magnetic field is strong, LS coupling will break. So, one line will be split into 3 lines. So, whatever the line, whatever any line if you take, so it will all the time it in strong magnetic field it is split into 3 line, okay. It is split into 3 line. But if we use weak magnetic field where LS coupling exists, will not break, okay. So, then your quantum number is basically J will play role, and this splitting will be basically asymmetric, it is not symmetric because of Gj, Gj will be different for different J, okay. So, so here the splitting was basically symmetric in case of ML. So, that is why 9 lines equivalent to 3 lines, but here the splitting are not symmetric, it is asymmetric because of Gj, and you will get basically this line is a transition between J equal to 3 by 2 to J equal to half. This line will be splitted into 6 lines. This line will be splitted into 6 lines. Okay. So, this is called basically Zeeman effect, but it is called anomalous Zeeman effect. Okay. So, normal Zeeman effect and anomalous Zeeman effect. So, however, we will concentrate in normal Zeeman effect because in anomalous Zeeman effect there are a lot of lines and it is difficult to resolve them. You need higher resolution of your spectrometer. So, in our laboratory we will demonstrate normal Zeeman effect. Okay. So, I try to explain what is Zeeman effect, and that we will demonstrate in our laboratory. So, in laboratory generally people use cadmium or mercury source, okay, to show the normal Zeeman effect. Now, why this cadmium or mercury it is used? So, to understand that one, here you can see cadmium basically it is a wave, this atomic number is 48 and electronic configuration is this is the krypton configuration, inert gas krypton, helium, neon, argon, krypton. So, 36 D410 5s2, and for mercury it is 80. So, this is its xenon configuration, and then after that 4f14 5d10 and 6s2. Okay. So, what you are seeing here, so all subcells are filled. Okay. So, that means these are ground state. In ground state, total L, total angular momentum, orbital angular momentum L will be 0, and total spin angular momentum will be S will be 0. So, L is 0 and S is 0 in ground state. So, LS coupling, there will not be any LS coupling. So, in both cases in ground state there will not be any LS coupling. So, that is why we can use small field to see the normal Zeeman effect. So, if LS coupling is there, to first you have to break it. So, for that you need basically very high field, and in laboratory we use the electromagnet, and then electromagnet generally it is a maximum field, it can generate it 2 to 3 Tesla. So, 2 to 3 Tesla for normal Zeeman effect is not enough for most of the atoms, but in this case less than 1 Tesla is enough because this LS coupling is not there, okay, in ground state. So, now in our experiment we will use mercury source. So, 6s2, okay. So, this 4 F14 and 5 D10. So, these electrons are more tight in the atom, but comparatively this S electron is it is the outermost electron, and it's excited to excite it, it's you need less energy compared to other electrons. So, in ground state, so we can think that this system have two electrons which we can which we can easily take in higher energy levels. So, for that we need less energy, external energy you have to give to the atom, then only electrons will go to the higher energy levels. So, that we tell this atom in excited state. So, in ground state, so electrons, two electrons are in 6s. Now, so one of these electron can go to the 7s electron, 7s, next one is 7s. So, 6s and then it can go to higher energy level 7s. Okay. So, in excited state, one electron is in 6s state and another electron is 7s state. Okay. So, 1 these two electrons. So, L, so for this pair of electron, L will be equal to 0 because L1, this for S is a 0. So, total L will be 0, capital L, and this total S. So, now when these two electrons in same S cell, so they have to be in opposite direction. Okay, one will be spin up and another will be spin down. So, S will be 0, but in this case they can be, both can be spin up and both can be spin down. Okay. So, S can be either 0 or it can be 1. Okay. So, spectroscopic term generally we write this 2s plus 1 L j with this notation. So, here S equal to when it is 0. So, 2s plus 1 is 1, L is 0. So, it is S, L is 0. So, it is S, and J will be, L is 0, S is 0. So, J will be 0. And for another state spectroscopic term we will get, so that is it is L equal to 0. So, S, then S equal to 1. So, it will be 3, 2s plus 1 it is 3 and this is 1. Okay, J will be 1. So, here we can get 1s0 and 3s1. Okay. So, this is here 1 and this 3, these are called basically multiplicity. So, this state we tell singlet state and this state we tell triplet state. Okay. So, now from this ground state, if atom goes to this excited state, and generally in excited state it stay very very small time, generally after 10 to the minus 9 second, okay, it come back to the lower energy or it jumps to the lower energy. Okay. So, it can jump to the again this state or it can jump to the this 6 S1. So, one electron was there and another electron from 7 S1 it can go to 6 P1, because 6 P1 have it's also is vacant. Okay, higher energy state 6 P1, yes, I think so. Is 4 7. Okay, so lower energy from 7s to the 6p is a lower energy. So, it come to 6p state or 6 S state. Okay, 6 S state. So, say it is going to the this state 6 S1 and 6 P1. It can go in many states, but this I have taken an example. So, say from here it is going to there. So, this is the lower energy state. So, in this case L is total L will be 1, because S for S L is 0, L1 is 0, and for this P L2 is small L2 is 1. So, capital L total L it will be 1, and S again spin, both spin half. So, both can be up, or one can be up, one can be down. So, S it can be 0 or 1. Okay. So, L is 1 means I will get P. So, for S equal to 0 singlet state, and J will be 1, L 0, L 1 and S 0. So, P 1. So, 1 P 1, then we will get triplet state 3 P. Now, S 1 and L 1. So, J will be 0 1 2. So, 3 P 0, 3 P 1, 3 P 2. Okay. So, in mercury, so basically so you can see, you will be able to see the transition among this whatever spectroscopic terms we are telling. So, this all will have different energy. So, they have energy levels. Okay. So, this each one will have different energy. So, there will be transition from either from here. So, this state to the any of this, or this state to the any of these. Okay. So, because of this transition you will get spectral lines. Okay. So, let me show you the transition. And so, as I described that, in case of mercury, in case of cadmium also, you will get singlet state and triplet state. Singlet state and triplet state, singlet state S equal to 0 and triplet state S equal to 1. Okay. So, if you calculate all sorts of excited state, okay, so just I have shown you one. So, 1 H0, 1 P1, 1 D2, 1 F3, this will be the singlet states. 3 S1, 3 P0, 3 P1, 3 P2, then 3 D2, etc. I have not written. So, so basically this spectroscopic terms you will get for this mercury. So, their energy levels, if I here, so 1s0, so 1s0, so energy level 6s, 7s, 8s. For 1p1, so this is 6p, 7p, 8p, 1d2, so this 6d, 7d. So, this way these energy levels are arranged. Similarly, here for triplet state 3s1, so this is 7s, 8s. So, this is 6p. Now, for 6p basically 3p0, 3p1, 3p2. So, here I have written 6p means 6p, there will be 3 triplet state, there will be 3 triplet states and their energy are different. Okay. So, if I just consider the transition between 7s to 6p, as I told, this one electron, say one electron it is in 6s1, another electron it has gone to 7s, and from there it is coming back to the 6p. Okay. So, then there will be transition between these two, means 3s1 to 3p0. So, you will get these spectral lines, its wavelength is 404, and then you will you may get the transition between 3s1 to 3p1, okay, 3p1 here. So, this transition is wavelength is 435, and then also you may get transition 3s1 to 3p0, transition between these two. So, its wavelength is 5, 4, 6. Okay. So, this type of there are many transitions. So, here I have taken one example. So, now here this is very strong line, intensity is very high. So, this one wavelength is 546. This in Mercury, these the prominent spectral lines, green spectral lines. Okay. So, we will take in our experiment, we will select these spectral lines without any magnetic field. So, these the spectral lines we will see its the wavelength is 546. Okay. 546.07 nanometer probably. So, I have written approximately. So, this is the green line we will select for our experiment from Mercury source. So, what is the origin of this line? So, that I try to explain. So, this is a single line, spectral lines. There will be many spectral lines. Out of that we will use filter and we will select this green line for our experiment. Okay. So, I think I will continue in next class. Thank you for your attention.